Thank you for the invitation. I love coming to Lumini, even when it's cold like this. Okay, so the Farrell-Jones conjecture is something that people in high-dimensional manifolds are interested in, and I regard geometric group theory as being a subject that might prove the Farrell-Jones conjecture for, at least in the case of some classes of groups that we're interested in. So I'd like to start this by giving a little mini course on high-dimensional manifolds. Not that I'm an expert, but that's all you get. So, okay, so as far as I'm concerned, the high-dimensional manifolds are about the following question. You're given so all manifolds in this lecture are going to have dimension at least 5. This is like in Reed's talk, that all groups are finitely generated. So here, everything is going to be dimension 5 and higher. So we fix one of these manifolds M. It's a closed manifold, and everything is going to be topological. You can ask this in the other categories, like smooth and PL, but topological is the simplest, it turns out. So it's a closed manifold, and it's greater than or equal to 5. And then there is something called a structure set of M. Okay, so how is it defined? Well, you look at all homotopy equivalences from a manifold of the same dimension n, closed manifold, to M. So this is a homotopy equivalence. And then you mod out by a certain equivalence relation. And you define this relation just in the same way that you define Teichmuller space. So if you have two of these, right, so there's F1 and F2, they're going to be equivalent if you can find a homeomorphism here. So this is a homeo, so that this triangle commutes up to homotopy. Okay? That's the equivalence relation. So it's somehow it's the set of all manifolds homotopy equivalent to M, up to homeomorphism. And you want to, somebody hands you a manifold, you want to say what this is. Okay, that's the goal of high-dimensional manifolds, of the theory. Okay, so the goal is to, well, this is really the holy grail, right? You're never actually going to be able to answer this, but the hope is that you can give some, maybe in some important cases, or you can give some kind of a procedure for understanding what this set is. So compute S of M. Okay. So notice that there are some special cases that we already know. For instance, when M is a sphere, then the Poincaré conjecture states that this set consists of only one point. Okay, so what are some methods in high-dimensional manifolds? Well, there are two main tools. Okay, so there are two main tools. One is the H-cobordism theorem. And how does that go? Well, you have some manifold with two boundary components, or you have two. You think of having two manifolds of dimension n, and they're connected by this manifold of dimension n plus 1. And everything is compact here. So you have m1 and you have m2, and you assume that these inclusions are homotopy equivalences. And you'd like to know that the whole thing is a product. And as everybody knows, there's an issue. There's an obstruction. So is this a product? Okay, so yes, if a certain obstruction called the Whitehead torsion, so tau, in a group that depends on the fundamental group. So G here is the fundamental group of all three of these manifolds. If this obstruction is 0. Okay, so this is a typical example. You have some method and you succeed modulo some obstruction being 0. Okay. Okay, so this is one. And then the other method, the other important method is surgery. Let's see if I can do this simultaneously. Oh, I cannot do it simultaneously. Okay, so the other method is surgery, and the setting is that you have a map from some manifold M to a manifold. Maybe I should call it N, as in you have a map like this, and you only assume that it's degree 1. Now I should say there. I'm going to be lying a bit in the lecture. I'm not going to. I'll suppress some technicalities, and in particular, there's more structure here. But anyway, for the first, if you've never seen this before, this is good enough. So okay, so you have a degree 1 map between two manifolds, and in particular, this degree 1 maps induce epimorphisms in homology, for example. And so the idea is now you want a process that transforms N to a manifold that's homotope equivalent to M. Okay, so surgery is a process that kills the kernel and transforms N to N prime, and together with the map, so that this is a homotope equivalence. Okay, so the schematic picture is something like you have here's your N, and here's M, and you imagine that this map is sort of killing a handle, and you find an embedded sphere in N that represents an element in the kernel and homology. This is some kind of a cycle that dies under F. And then you perform surgery. So the new manifold is just something like this. Okay, so this is your new manifold. And in this case, you've succeeded, but in general, you might have to do more surgeries. And you keep doing this, and then you might get stuck. And one obstruction is the signature. So like if the manifold has dimension divisible by 4, then you can look at the intersection pairing in the middle dimension. And this intersection pairing is symmetric, and it comes with a signature. And the process of surgery does not change the signature. So if the two manifolds don't have the same signature to begin with, then you're not going to succeed. And in general, if the manifold is not simply connected, there may be additional obstructions. There's some kind of a quadratic form here, but it's the quadratic form over Z in the simply connected case. If there is a non-trivial fundamental group, then this quadratic form lives in. It's a quadratic form over the group ring. So there's an obstruction. And the obstruction group here, it's just like the Lecce group. This is called Ln of Zg, the group ring. So this is some kind of a space of quadratic forms over Zg. So obstruction in there. Okay, so to cut the long story short, there are these procedures for kind of answering this question. I mean, so how would you use these tools to say something about the structure set? Well, you have some manifold N, homotopy equivalent to M, and you'd like to maybe show that they're homomorphic. Well, so in the first step, you want to make an H cobordism between them. In other words, you want to construct a new manifold that's homotopy equivalent to maybe the product. And so for that, you use surgery. It's some kind of relative version. Here I stated the absolute case, but there are relative versions. And so you can hope to use surgery to construct an H cobordism between N and M. And then if you succeed in that, then you can hope to use the H cobordism to prove that it's a product, and therefore N is homeomorphic to M. But there are all these obstructions along the way. Okay, and so what is the philosophy of the Farrell-Jones conjecture? So whenever you have, so these obstruction groups all depend on the fundamental group G. And so you have, so given an obstruction group, so to a group G, you're associating, well, I'll just call it O of G for an obstruction group. This could be the Whitehead group, or it could be one of these L groups, or there are other kinds of obstructions. There exists. So the conjecture is that this is somehow, these obstruction groups are the simplest possible. You know, so what does simplest possible mean? You know, this is not something exotic. This is something that, you know, the simplest thing that can conceivably work. Okay, so there exists a generalized homology theory. Such that when evaluated on O of G, on KG1 gives O of G. So these obstruction groups are defined only on groups. They're not defined for all spaces. Or if for a topologist, you could say they're defined on spaces which are KG1. They're not defined on non-aspherical spaces. But we are conjecturing that, in fact, you can extend this, whatever this is, you can extend it to all spaces and get a homology theory. And then if you have that, then in principle we know how to compute, right? We can cut it into pieces, and you can use Meyer-Vietoris and long exact sequences and all the wonderful things in Hatcher, right? And so that's what it is. That's really the Farrell-Jones conjecture. I can maybe just to impress you, I can write some, you know, the formal thing, but okay, so it's like this. Okay, so this is the way to denote a generalized homology theory. So there is something called a spectrum. So you need, that's also in Hatcher, by the way. If you have a spectrum, then you have a generalized homology theory, and this is supposed to be isomorphic to Ln of Zg. Okay, so there's some map. Now it's hard work to actually define the spectrum here and to define this map. And I think the top of the line effort in this direction is a paper by Davis and Lück. It's about 50 pages long. It's really hard work. And, you know, they define the spectrum, and they define this map. This is called the assembly map. You somehow in your mind you imagine having this big space KG1, and you're cutting it into pieces and computing homology with pieces and then putting back together. So that's the assembly. Okay, so that's. And then we conjecture that this is always an isomorphism. So here we have some homology theory. You can stick in any space you like here. And when you stick in KG1, the conjecture is you get this. Okay. Now, I'll tell you some consequences. You're supposed to be impressed by the consequences. If you know, assuming you know the conjecture for a certain group. Well, so let's compute some of the structure sets. Oops, what is this? This. Okay, so the first amazing thing about the structure set is that it's an abelian group. That's not obvious from the definition, and it's also very hard work to establish that. And it was actually realized fairly late in the development of surgery. Okay, so consequences. So, well, so first of all, so if G is torsion free. Okay, so I'm sweeping various technicalities under the rug. So this is not, technically this is only for torsion free groups. When the group is not torsion free, there is something a little more complicated, which I won't get into. Okay, if G is torsion free, the structure set and so pi1 of m is G, then the structure set S of G is isomorphic to, so it's an abelian group, okay? And it's isomorphic to a relative homology of, the same homology. So Hn plus 1 of Kg1. In surgery, they like to call this Bg, but I'll stick to Kg1 M. Not S of G, S of M, sorry. Okay, so the structure set of M is this relative homology. So, in homotopy theory, every map is an inclusion, right? So M, you can think of M as being a subcomplex of this Kg1. And then you take this relative homology. And that's what the structure set is. Okay? So let's do some examples. Oh, I have to tell you, when you're faced with a homology theory, you have to ask what the homology of a point is. And I'm going to lie a little bit here, but it's all in good cause. So let's see. So the fact, false fact, homology, or fake fact. Okay, Hn of a point. This funny homology theory. This is going to be Z when n is greater than 0 and congruent to 0 mod 4. Okay, and it's going to be Z2 if n is greater than 0 and n is 2 mod 4. And is 0 otherwise. Okay, so this is, some of you who've maybe thought about simply connected surgery, for example, will recognize this. This is the signature, and this is the ARF invariant. Okay, so let's do some computations now. So, example, let's take the sphere. M is Sn, right? So compute the structure set of Sn. Well, this tells me I'm supposed to do Hn plus 1. And then the group is trivial here. We know the Farrell-Jones conjecture holds for the trivial group. Okay, and M is the sphere. So here I need some contractible space that contains the sphere. So that'll be the disk, plus 1, and then L, right? Now, long exact sequences and so on, right? This is just like in Hatcher. You do this, inductively on n or whatever, and you end up with h0 of the point, which is 0. So I just proved the Poincare conjecture for you. How many times did that happen? Okay, another example. Suppose M is aspherical. And suppose we also know that that pi1, so G equals pi1 of M, satisfies Farrell-Jones conjecture. Okay, let's compute the structure set. Well, here, instead of the Kg1, I could use the manifold itself, because it's aspherical. Okay? And then Hatcher will tell you that this is 0, no matter what L is. So this is the Borel conjecture. Right? Any homotopy equivalence between aspherical manifolds is homotopic to homeomorphism. And then just to convince you that not everything is 0, if I take M to be something like S4 cross S4, I won't get into the calculations, but here it turns out it's not. So this is also simply connected. S of M is, well, it's H9 of, well, I don't know, something contractible S4 cross S4. And this, I don't actually know exactly what it is, but it's something like modular torsion, it's something like Z squared. Okay, so they're manifolds homotopy equivalent to S4 cross S4. They're not homeomorphic to S4 cross S4. So this is really, I guess, I could say Sullivan's thesis. Okay. Now, of course, this is not, I mean, the point is that all this work is all built into the machine. You know, it's not that these are independent proofs, right? This is just part of the machine. Okay, so this is enough propaganda about why this is good. Now, let me tell you what's known. Okay, so here we go again. No, I can use this, right? Okay, what's known? Okay, so they cleverly set up the theory so that you can actually pass to subgroups and finite index supergroups. So there's some class of groups that they define. Okay, so FJC is a certain class of groups satisfying a strong version, and I won't get into of the Farrell-Jones conjecture. I won't get into the details here. The point is that you can, you can stick in, instead of just talking about rings here, you can talk about more general objects, just including categories. You can talk about, L groups with coefficients in the category and stuff. But when this is properly set up, then in fact, this class FJC is closed under taking subgroups. So that's important, and finite index supergroups. Yeah, when you prove the Farrell-Jones conjecture for mapping class groups, right? How often are you going to have a manifold whose fundamental group is equal to the whole mapping class group? Right? Not very often. But the point is that this then holds for any group that can be embedded in the mapping class group. Okay, so that's a lot of groups. Okay. Okay, so the first fact, it's so these extensions. So if I have a short exact sequence like this, and this map is called pi. Oops. Now I'd like to know that if if Q and N are in the class, then G is also in the class. Unfortunately, that's not known, or maybe it's even false. Well, it can be false because there are no, for all we know, all groups are in this class. but it might be unknown. But anyway, let's see. So, but what you know in addition is that assume for every virtually cyclic group Z in Q, pi inverse of Z. So that's it's a subgroup of G, which is bigger than N, right? If I'm pulling back the trivial group, I would get N. But here I could get something a little bit bigger. But suppose that this is in my class FJC, okay? Then G is also in FJC.
You have to assume Q is what?
Yeah, I think yes. I do want to assume it for. I do want to assume it for Q, yes. Q is in FJC. Yeah, otherwise, pi could be an isomorphism. Right? Okay. All right. Okay. Okay, so this is a theorem of Wenger. So the all virtually solvable finitely generated groups are in FJC. Now I should say that for some subclass here, this is not too hard to show. Like for abelian groups or polycyclic groups even. What makes it hard is this whole virtually solvable class. Okay, now we come to sort of the main, the main thing that they give us. if you're in geometric group theory, we want some method. What do we need to prove about the group, right? We don't know. We don't want to worry about spectra and such. We want something concrete. So here it is. This is the theorem of Particles, Lück and Reich, and it's an abstraction of what Farrell and Jones did. Okay, so let me state it, and then I'll make some comments. Okay, so you have a group G acting on a space which is a Euclidean retract, and this concept came up earlier in Bain's talk, I think. So this is just some finite dimensional contractible and locally contractible space. Something that's, think ball, for example. Okay, it would be just a usual ball, and G is acting on it. And script F is going to be the class of virtual point stabilizers. So these are subgroups of G which virtually fix a point. So they have a finite orbit. Some orbit is finite. Virtual point stabilizers. Now you assume that every group, every F in F is in FJC. And then there's a sort of a technical thing which I think I'll postpone as much as I can. So the action is what's called finitely F amenable. Okay, so this is some kind of a technical thing about what the action has to look like. But then the conclusion is that the G is in FJC. Okay, so I'm going to give you some examples of this. Okay, top or down? What's this? I see, it just doesn't want to do it simultaneously. Okay, so let's say we have a free group. How would we prove the Farrell-Jones conjecture for a free group? Using this. So we need a space, and then we need this X. Okay, so what should X be? Does anybody have a guess? That's right. It has to be a compact though, so we have to compactify it. So we get a dendrite. And that's an ER. And then you have to check something, and I didn't tell you what you need to check, but it turns out it holds. So here's an example. So a free group is in FJC, and the proof is the free group is acting on the compactified. So T is the Cayley graph. And you compactify it by adding the ends. So this is T union boundary T. And then you check that it satisfies finite F amenability. And that's not a trivial thing. I mean, in the presence of negative curvature, then the keyword is geodesic flow. You have to do some, it's about constructing open covers with a certain property. And you use the geodesic flow to flow your initial open cover to make it correct. I don't think I'll get into that today. Okay. What else? Fn cross Z. Okay, that'll be important. That's our first example of a free-by-cyclic group. And so this satisfies the Farrell-Jones conjecture by this exact sequence argument. I can put Fn as Q. Fn can be Q, and then Z can be the kernel. And then this condition holds because these groups that you get by pulling back abelian subgroups, or cyclic subgroups, are all abelian. So they'll satisfy Farrell-Jones by number 2. Okay, so this is from Fn and from the previous board. Okay, surface groups. Okay, so this is really Farrell-Jones. I mean, they proved this, and you do it by acting on the compactified hyperbolic plane. Okay, that was their absolute retract. And then Bartels, Lück, and Reich generalized this. They abstracted what you really needed here. And you don't need a ball. You can get away with Euclidean retract, so you can work with things like dendrites. Okay, then another example. So this is a theorem of Bartels, Lück, and Reich. I mean, that's where they came up with it. Property there, Bartels, Lück, Reich. So hyperbolic groups. Okay, so here they use the Rips. So this already also came up yesterday, right? The action is on the compactified Rips complex union the boundary, and that's an absolute retract. And the action, it turns out, the action satisfies those conditions. Right, the stabilizers here are just virtually cyclic, for example, just like in the surface case. And the virtually cyclic groups satisfy the Farrell-Jones. And then you have to check the finite amenability. Okay, another example, and that's work with Bartels, mapping class groups. They also satisfy Farrell-Jones conjecture, and the strategy is to consider the action on the compactified Teichmuller space, which is a ball. And the stabilizers are, roughly speaking, just simpler mapping class groups. So you argue by induction that mapping class groups satisfy Farrell-Jones. And so when you have a surface, you're already assuming that simpler surfaces, the mapping class groups satisfy the Farrell-Jones. And then you have to check that's sort of the hard part. You have to check this condition of finite amenability. Okay, here's a very useful thing that was proved only recently. It's number 4. This is Svenja-Knopf. If you have a group acting on a tree, so this is a tree, acylindrically. Okay, and this was also already defined, right? So if you take 2 points that are sufficiently far apart, then the common stabilizer is trivial. Okay, so I won't write that down, but that's the, I forget who defined this. Somebody did. Anyway, it's yesterday. All right. If all stabilizers are in FJC, then in fact the group is in FJC. So for example, free products. Some of this was already known, like so this case of free products was known, and various other things. But this is a very clean way of summarizing what, and the proof here is sort of generalizes this our first example when you have a free group acting on the compactified tree. So here, G is going to be acting on the compactified tree, and you run this program for this action. Okay, so what are some corollaries here? See, observer's topology. Observer's topology. So, see, I forget, was that in Emily's talk? Yes, although she didn't say those words, but it was implicitly there, right? So you have observer's topology. So it's like, if you have a tree, I'll just give you an example. So let's say your tree. So the issue here is that these trees are not locally finite, right? So that you can have a vertex of infinite valence. So the simplest tree to think about is just you take a union of countable many rays like this that have a common endpoint. So what should the compactification of that be? Well, it's this. In other words, if I take a sequence of points that maybe even go to infinity on individual rays, but the sequence doesn't stay on the same ray, then that sequence will converge to the base point. Okay, so that's what this T bar is. Okay, so 3 manifold groups. That's a corollary. 3 manifold groups are in FJC. So this was proved originally by Rushton in 2004. But the proof, is because of all these things that were proved fairly recently, is now very simple. So what's the proof? Well, for geometric manifolds, it's already on the board. Depending on the geometry, you just look it up. So, for example, I skipped something. I skipped something important. I'll have to go back to this. It belongs here. This is where I meant to put it. It's it's called an example, but it's actually a very significant theorem due to Bartels that in fact relatively hyperbolic. So if G is GP, I think that was the notation yesterday. So relatively hyperbolic, and all P in P are in FJC, then G is in FJC. Okay, so if you're hyperbolic relative to a collection of groups where the Farrell-Jones holds, then in fact Farrell-Jones holds for the group. And this is actually a quite clever construction. I mean, it's roughly speaking, you want to use the space that or the boundary that was constructed by Dahmani. But in addition, it's not enough just to have the boundary. You also need the whole Euclidean retract. So you need some version of the Rips complex. And you cannot use the full Rips complex because that will be infinite dimensional. So there's some kind of a relative Rips complex that turns out to be finite dimensional and still contractible. And then you study the action on that space, and you check the finite FM amenability holds. Okay, so relatively hyperbolic groups are good. And so we have, if the manifold is not geometric, then we look at the pieces, they all satisfy Farrell-Jones. And so what needs to be said is that, so there's a theorem of Wilton and Zaleski, and that was also mentioned already, that the JSJ, so Wilton, so proof, Wilton, Zaleski, that the JSJ tree is acylindrical. It's 4 acylindrical, to be more precise. Okay, and you know it for the pieces, and so plus the stuff before, right? So plus whatever should be pretty clear now. Plus geometrization, plus Farrell. Okay. Okay. There are more things known, and they don't all. I mean, this is not the only method to prove Farrell-Jones. There are other things, and I'll just state a couple of classes of groups that are known to satisfy Farrell-Jones using a method different from that one.
I'm sorry, for free manifolds, are you assuming they are spherical?
You don't have to. I mean, the free products are.
This holds also for free products?
Yeah, free products are also good. That's also by the. I mean, that was also known before. But if you want, you can use Knopf for free products. Right? The free product gives you an acylindrical tree. Right. Okay, so this is fact number 5. So cat0 groups. This was Bartels and Lück. And then also lattices. And any lattices you like. So these are lattices in virtually connected Lie groups. You can't get more general than that, right? This was, let's see. Okay, this ends my survey of what's known. Maybe I should ask if there are any questions. Take a deep breath. But anyway, so here's a new theorem. Okay, so then maybe I'll call it 6. And so if f from fn to fn is an automorphism, any automorphism, then G is Fn like F is in FJC. Okay, so we already saw an example of this when F is identity, right? So it's a good starting point. So these are groups that Emily talked about, except for her this was always hyperbolic. When this group is hyperbolic, we already know this is true by the stuff above. And so the issue here is, what about the general case? Okay. Now I have to make a decision. Should I give an outline of the proof, or should I tell you what finite f amenability means? What do you think? I could try to do both, but I think I'll run out of time for on the second one. Okay, quick outline, and then I don't mind running out of time on the definition. You can look that up yourself. Okay. Let's see what else. Is something coming? Yes. Suspense. Oh, it got stuck. Oh, I see this was going up. I see. The wrong orientation. Okay. Okay, so the key case is that of a polynomially growing automorphism. So there are really two steps. The second step is just quoting somebody's theorem. In fact, the proof here is not very hard. It just uses, we don't actually have to analyze any sort of action. It sort of follows from the structure theory of automorphisms and what's known. But it does answer a question by Lück, so it's worth writing. Okay, let's see. Okay, so the sketch is, so there are two steps. So so case one is that f grows polynomially. And there is a whole structure theory of these things, and an example is something like A goes to A, B goes to BA, or B, say something like that. C goes to C, A, B, for example. Okay, so there's an ordering of the. You can realize f. So I'm allowed to pass to a power. See, because of this passing to finite index supergroups. So up to a power. F is realized as a homotopy equivalence on a graph with edges, E1, E2, etc., EM. So there's an ordering of the edges, and so that f of EI is equal to there's an EI in the middle, and then you have some word here in some word in the E1 through EI minus 1. And over here you have some other word in E1 through EI minus 1. So it's like an upper triangular matrix. Just like this, right? And then the point is that the group G, the semi-direct product, splits over Z. So Emily mentioned that too yesterday, although she liked the examples where there is no splitting. But here we like splitting. Splits over Z, right? How do you see that? Well, you have your A, B, and C. This guy C is on top, and you can take you can adjust the map F so that it, for example, fixes some arc inside C, pointwise, and then what's left of the loop does it does the work of crossing appropriate edges and so on. And so when you suspend, you're crossing this with 0, 1 and then gluing by this F. You're going to see an embedded annulus, right? This arc will come back to itself and it'll give you an embedded annulus. That annulus gives you splitting over Z. And you look at the action. So T is going to be the Basset of that splitting. Now, unfortunately, this may not be acylindrical. What happens is that okay, let's go over here. Every edge stabilizer, of course, is isomorphic to Z. And if you take two different edges, they might either have the same stabilizer, the same Z, or the two Z's will intersect trivially. Okay, so this gives you some kind of equivalence relation on the set of edges. Okay, so this is not acylindrical. T is not acylindrical in general, but consider the equivalence relation. There are two edges, say E1 is equivalent to E2, so these are edges. If they have the same stabilizer. They're always infinite cyclic groups. And then what happens is that the equivalence classes form trees. So you get a picture like this. There's one equivalence class, it's a tree, and there's another one over here, it's a tree, and of course they can intersect in at most a point. They cannot have the same edge in common. And then there's maybe another one, and so on. And then what you do is, so this is called the transverse family, and you can form a skeleton of the transverse family. That's also a standard construction in the subject. So let S be the skeleton of this collection. So it's also a tree. It's bipartite, and so the vertices are there are two kinds of vertices. There are equivalence classes themselves. So there's an orange vertex, there's a blue vertex, and so on. And then there are also there are vertices that come from non-trivial intersections between the equivalence classes. So equivalence classes and then non-trivial intersections between the equivalence classes. Okay, and then edges are incidents. Okay, so that turns out to be a tree, and the action on that tree is acylindrical. So this is acylindrical. And you compute the stabilizers, and the stabilizers are going to be either free group cross Z, or they're going to be simpler free-by-cyclic groups where where you have fewer edges. Like here in the original tree, there's a vertex stabilizer that's a free-by-cyclic group coming from this automorphism, where you cover up the top letter, right? And so by induction, you know that that's already in FJC, and so then you apply Knopf, and then you're done. Okay. Right. Okay. So now the only thing left is to tell you what finitely F amenable means. And this is, I sort of decided, there are two things. There's a clever short definition, and then there's the actual working definition, which is more complicated, but that's how you think when you want to prove, when you actually want to use it. So I decided to use the short version. but also, Also, I want to compare it with other similar sounding properties, and there, I think this is worth doing. Although I'll have probably run out of time. Okay. So, yeah, so there are various properties that have word amenability in them. And they all have very similar definitions. Okay, so let me just make sure I don't get this wrong. Okay, so this is going to be called asymptotic dimension, boundary amenability, and finite F amenability. Okay, so the common feature here is, so we have a group G, and then we also have a space, and this is going to be compact Hausdorff. And of course, in our situation, it's much better. It's a Euclidean retract. And E is going to be so G is going to be acting on both X and E, and E is going to have an equivariant, the G equivariant metric. Okay, so that's the setup. We have two spaces in the group acting on both spaces. X is compact and doesn't necessarily have to be even metrizable, and E comes with an equivariant metric. Okay, and then we say that a sequence of functions, of continuous functions from X to E, okay, so this is a sequence, 1, 2, so on. So we'll say that this is asymptotically equivariant. Equivariant. If the soup over X in X of the distance between Fn of Gx and G Fn of X goes to 0 as n goes to infinity. Okay, so if it was equivariant on the nose, this would be 0. But you just want to know that somehow as n gets larger and larger, we are more and more equivariant. Okay, and then now I can give you these definitions, and it's really, it's deceptively easy. Okay, so definition 1. So the action of G on X, this is compact Hausdorff. Okay, so this is topologically amenable. If there exists Fn from X to the space of probability measures on G. So this is our E, and the metric here comes from L1 of G. Right? You think of a probability measure on G is an element of L1. Okay, so if there exists Fn that are asymptotically equivariant. Okay, and then the group is boundary amenable if such X exists. So G is boundary amenable if there exists X, if there exists G acting on X as above. Okay, definition 2. So the action of G on a compact Hausdorff space is n amenable. N is a number here. If there exists Fn from X to so this is the n skeleton of the full complex, full simplicial complex on G. In other words, you take every possible pair of n plus 1 tuple of points in G, and you put a simplex there, and that gives you a simplicial complex. And you have to be able to come up with this sequence Fn, just like in the definition above. notice that this is stronger. I mean, if any one of these things is also, I mean, a point in here is going to have barycentric coordinates that give you a probability measure on G supported on n plus 1 points. So if you have this, then you also have this, right? And it's a theorem of Günther, Willett, and Yu that as asymptotic dimension of G is less than or equal to n if and only if the action of G on, now are you ready for this? This is the stone-check compactification of G is n amenable. So somehow the stone-check compactification is the universal thing here. If you have some x, right, then you also have a map from, x is, you can think of x as being some compactification of the group by taking the closure of the orbit or something, and then the stone-check compactification maps to it. So if you have some x, then you always have the stone-check compactification. Okay, so now in the remaining 3 minutes, I can tell you what the finite FM amenability means. So it's some variant of this, right? But the main difference is that we have some family of subgroups, and they're supposed to be fixing points. So we don't really expect maps like this where the action is free, because we have non-trivial stabilizers. Okay, so definition 3. Okay, so F is going to be a family of subgroups of G, and it's supposed to be closed under conjugation subgroups and finite index supergroups. And now you form, so we're going to imitate this construction here. But instead of building a simplicial complex on all of G, we're going to take left cosets of the elements of F. So we take S. S is going to be our vertex set, and we take that to be the disjoint union of all elements in this family of these cosets. All right, so if the class F consists only of the trivial group, then you would just get G, just like in this definition here. But here you have more stuff. You have for every point, for every group in F, you have a point in the set S that's fixed exactly by that group. Okay, and then we take delta FG. This is going to be the full simplicial complex on S, and then we take the n skeleton. Delta Fn, this is the n skeleton. Okay, and now we can define, maybe I'll go over here, the big definition. So the action of G on X, which is still compact Hausdorff, but remember, in reality we want X to be a Euclidean retract. But you can make this definition for me. So if there exists Fn from X to delta n, what am I defining? So it's NF. So G. So this is NF amenable. This action is NF amenable if there exists Fn like this, which is asymptotically equivariant. Okay? And then finitely F amenable just means for some n. So the action, so G on X is finitely F amenable if n F amenable for some n. Okay, so you can see, I mean, you can compare these properties, and they're all interesting in manifold theory. So these two imply, if you know that the group is boundary amenable, that implies the Novikov conjecture, which is some weaker version of the Farrell-Jones conjecture. And likewise, if you know that the group has finite asymptotic dimension, you can also deduce some slightly stronger version of the Novikov conjecture. And then this is what you need. But you can compare how these things differ. Well, here it can be any old compact space, and the action on the Stone-Check compactification doesn't have very many stabilizers. I don't know if it's actually free, but or you can also think about the profinite completion if you want. That's also a potential X, and it also doesn't it's not going to have a lot of stabilizers. But on the other hand, in our situation here, X is a Euclidean retract, so every Z is going to have to fix a point by Brouwer's fixed point theorem. And so there's some kind of a tension here going on, that you have your X is a nicer space, but you have to live with these stabilizers, and then the space on the right is going to have to, it's not going to be as nice as just this. You have to kind of modify it to allow for these stabilizers. And so it's a game you have to play, but I think this is somehow what they're handing us. The high manifold people are telling us, think about this, because there are groups you think about all the time, and try to prove it for your favorite group. So I think I should stop. Thanks.
Are there any questions for Mladen?
So for out-FN acting on rectified outer space,
So out-FN is, that's a long story, and that's something I'd like to see done before I retire or something. But so the first problem was that the usual compactification is not Euclidean retract. So then there is this work I did with Camille that finds a different compactification, which in fact is Euclidean retract. So that's sort of a starting point. You could ask if that action satisfies this, and it might. I don't know. There is some kind of a blueprint for how you should go about it, but there are too many at the moment. Too many steps that we don't know how to do. Yes.
What's the status for elementary amenable groups?
I think for our elementary amenable groups, I think it's closed. This class is closed, and they're taking direct limits.
right? Yes, I wanted to.
So I think then it's you have solved. Then I think you're in good shape. I don't. I would have to think through the definition, but I think then it follows from this exact sequence business, doesn't it? I don't know. I can't think of my feet, but. Okay, I don't know. Then there is the Krophover class. So it comes to my no Farrell-Jones for the Krop. Okay, I don't know. I would guess that the answer is yes, but I don't know for sure.
Is anything known about ascending extensions of free groups?
Well, that's something that one should look at after this. Yeah, because what you're using is some sort of a. Oh, didn't I say what step 2 is? I didn't say what the step 2 is in the proof. Okay, so I should say it now. The step 2 uses the theorem of Gautier and Lustig that says that in general these free-by-cyclic groups are hyperbolic relative to subgroups that are themselves free-by-cyclic groups, but based on a polynomially growing automorphism. And so you put the step 1 together with the Bartels theorem, and then you get the Farrell-Jones. Sorry, I should have said that. But there is some sort of structure theory for injective endomorphisms, for example, and then one could try to do the same.